Hello, welcome back to video 2 of section 4.5. We'll start with a couple theorems. So theorem 411, let H be a subspace of a finite dimensional vector space V. Any linearly independent set in H can be extended to a basis of H. And I say here extended if necessary, which means that if it isn't already a basis, then you can chuck in some extra vectors until it becomes a basis. Yeah, as well, since V is finite dimensional, so is H, and sort of the obvious thing happens that the dimension of H is no more than the dimension of V. So this is telling us that dimension is, you can't. It's telling us sort of what we maybe we think already, that dimensions, you can't stack bigger ones inside of smaller ones. Okay, and this is sort of a build up to theorem 412, the basis theorem. So this says let V be a p-dimensional vector space where p is some number bigger than 1 or equal to 1. It says that it says two things. Maybe we'll label these things to distinguish the two things it's saying. So one, it's saying any linearly independent set of exactly p vectors is already a basis. So if you know the dimension already, and you have like half of it, you have the right number of vectors, and that it's linearly independent, then it's a basis. And the second statement is the same, is sort of related. Again, if you have the exact right number of vectors and they span, then it's automatically linearly independent. So it's sort of like there's the right number, there's spanning, and there's linear independence. This theorem is saying grab your favorite two. Yeah, grab your favorite two. Then it has to be a basis. That isn't quite true. This is saying fix the right number of vectors, and then linear independence gives you spanning, and spanning with the right number of vectors gives you linear independence. Happens to be true that if you span and you're linearly independent, then you have the right number, but that's the definition of basis. But that's one way of thinking about this. Yeah, if you have the right number of vectors of the two remaining conditions of a basis, right number of vectors and one of them implies the third. Yeah, okay, so let's talk about the dimension of the null space and column space of A. Yeah, so we've seen that the pivot columns of A form a basis for the column space of A. And so what this means is that the dimension of the column space is just the number of pivots. The number of pivots. Okay. Boom, that's not so bad. And then also we know that each free variable in the system associated to the augmented matrix of A with zeros in that rightmost row, each free variable corresponds to a basis vector of the null A. So then the dimension of the null space of A is just the number of free variables. Number of free variables in the equation AX is equal to 0. Okay, so let's look at an example to make this more concrete. If A is this 4x5 matrix, we want to find the dimension of the column space and dimension of the null space of A. So first we'll row reduce, and since we've done this so many times before, I'll let you practice out on your own, and you can check your answer. You ought to get 1 0 0 0 0 1 0 0 1 negative 2 0 0 0 0 1 0, and then 1/3 1/3 negative 1/3 1/3 0. Okay, so we get what? We can immediately get that the column space of A is the span of which vectors. And again, the easy mistake to make would be to say it's the pivot columns, but no, it's the pivot columns of A. So we say, okay, we've got column 1, 2, and 3. Those are the pivot columns of our row reduced matrix. That means we want columns 1, 2, and 3 for our basis of our column space. So really we want the vectors 1 0 4 2, 0 1 3 negative 1, and 5 4 negative 4 6. Okay, and that's telling us that the dimension of the column space is just 3. And what? For the null space, yeah, for x in the null space of A, what's true? Our x should be x1, x2, x3, x4, x5. Okay, and what equations are we going to get? It looks like we can express x1 in terms of x3 and x5. Looks like we can express x2 in terms of x3 and x5, and x4 in terms of x5. So it looks like our free variables, well, we'll write it all down and we'll sort out the free variables. Okay, so then what, x1 ought to be -1x, just negative x3, minus 1/3 x5. X2 looks like 2x3 plus 1/3 x5. X3 is free. I'm rapidly running out of room here. X4 is minus 1/3 x5, and x5 is free too. So we can pull out an x3 and get part of it -1, 2, 1, 0, 0. And then x5, what are we going to get? Minus 1/3, 0, minus 1/3, 1. And so this is telling us, yeah, a couple of things. The null space, null space of A is the span of these two vectors, -1, 2, 1, 0, 0. Oh. And -1/3, 1/3, 0, -1/3, 1. And so the dimension of the null space is just 2. Okay, and you might say, David, 2 and 3 makes up 5, and that happens to be the number of columns here. Is that a coincidence? And that's for next time. Okay, I'll see y'all with the last section, 4.6, next time. Take care, everybody.